Welcome you all. In this lecture, we are going to discuss about effect of capillarity on effective stress. In fact, this is the last topic in our effective stress chapter. So let us have a discussion on capillarity. See, many times we used to hear about capillarity in the physics, and you might be heard also about capillarity in fluid mechanics. In fact, you see, capillarity could causes tension. That means you see capillarity whenever you see surface tension. See, take one jar filled with water. If we insert a small diameter tube, the water will rises. So this is the phenomenon of capillarity that could happen in a small diameter tube. The same thing could happen in soils also. Whenever you see interconnected interstices within the soil mass, we have interconnected interstices. So this may not be exactly in circular cross section, but so these interconnected interstices, uh, they allow water to flow in vertical direction, especially in upward direction. So this could be, see, many times you see what this is the water table. Let me assume this is the ground surface. This is the position of groundwater table. So sometimes what happen, you see, due to capillarity, due to these interconnected interstices, when the sometimes you see because of this upward flow, so water is going to be enter beyond the zone of saturation. Generally, you see this is the groundwater table. So below the groundwater table, we expect soil is saturated. But due to capillarity, see this I would like to say, the capillary fringe is formed. This is the upward flow. I want to show you the symbol. Many times we use it to observe in books also. So this is, you see, this is capillary fringe. Here you see capillary fringe. So this is because of capillarity, the water is flowing in upper direction. So this causes a negative pore pressure. So this causes, if you see the pore water pressure, here you see this is the pore water pressure distribution diagram now. Many times we use it to draw pore water pressure distribution diagram. This is gamma of water into height of water. Now we are seeing this is minus. Why I'm writing here? See, because of capillary tension, so because of upward flow, this is could happen now. Minus gamma W into Hc. Somebody want to ask me what is Hc? Hc is the height of capillarity. Hc is the height of capillarity. This capillarity is due to formation of flow of water in the upward direction due to this formation of interconnected interstices, which leads to rise of water, saturation of water above the groundwater table. So this zone is also saturated now due to capillarity. Due to capillarity. So let me explain now. You see, I just now I shown you. See, this is minus gamma WHC. So this is the height of the capillary rise in soils. In soils also very interesting. We use it to found this phenomena because of tension. So negative pressure will form. So this is you see minus gamma W into S. You see many times we use it to calculate capillary rise using this formula 4 sigma cos theta by rho ZD HC is equal to where sigma is surface tension for clean water theta 0. Now one can see 4 sigma by gamma. So very interesting surface tension of water. Here you see it is 75 into 10 power minus 3 Newton per meter. Sometimes you see 10 power minus 6 8 Newton per millimeter at room temperature. So gamma of water, as you know, 9.81. If you substitute these values in this, Hc is equal to 4 sigma by gamma W into D, we will get an equation here. Hc is equal to Hc is in meter now, 3 into 10 power minus by dc. This is going to be in meter also. So this is diameter of the void. Here I am trying to call. So whereas in physics we used to call it is a diameter of the tube. Here it is diameter of the interconnected interstices that we are trying to call as void. So this small d is diameter of the void is in meter. But many times we used to observe Hc is equal to this is a popular formula point 0.3 by zero point 0.3 by d. But here you see HC is in centimeter. Let me tell you, here d is also in centimeter. So this is actually this equation came from this derivation. As I shown you, HC in meter is equal to 3 into 10 power minus 5 by dc, diameter of the void in meter. So if you convert in centimeter, you will get this equation. HC is equal to zero point 0.3 by d, where d is the diameter of the void in centimeter, where HC is in now in capillary rise in centimeter. So this is one numerical example that we are going to discuss now. So let us discuss now. Here you see, I have here you see a sand stratum. Here we have a sand stratum. Here you see the water table is at 2 meter. The thickness of the sand stratum is given. Here you see this is 10 meter. Thickness of the sand stratum is 10 meter, and water table, very interesting to discuss this, 2 meter below the ground level. You see the position of water table is 2 meter below the ground level. The unit weights of sand layer above and below the water table are given. You see gamma is given 17, and also below water table means gamma saturated is given 21. Now, the capillary rise above water table is 1 meter. See here, the capillarity is considered. In fine sands, the capillarity is possible. So, lesser the diameter of the void, more will be the capillary rise, because HC is equal to zero point 0.3 by D, where HC is in centimeter, D is in centimeter. So, as diameter of the void is decreasing, so capillarity rise is increasing. Here, you see, the height of the rise is 1 meter. Sometimes you see it is even 30 meter also. Now we need to draw total stress per water and effective stress diagrams. So there is a capillary rise above water table, that is 1 meter. Now this zone is also saturated. I want to tell you this is also saturated because of this upward flow. Uh, so this zone is also saturated. So this is capillary fringe now, zone of capillarity. Now let me tell you how to draw total stress. Here it is very important now. So here gamma into H1. Here H1 is 1 meter. I would like to call capillary zone as H2. This remaining portion is H3, that is 8 meter. Total H1, H2, H3 altogether is 10 meter. Now let me tell you gamma into H1, that is you see here uh, 17, 17 into 17 into 1. So one can easily write now. Here you see we have 17 above the water table. Unit weight is the 17 into 1. So now it is 17. So now here you see whatever you are seeing here is 17. Now let us move to the second position. Here you see this is section BB. So now we are at, here you see how to calculate total stress now. Here we have 17 into 1. That is continuing now. It is as overburden plus plus. Now you see this is also saturated. This zone is also. Now it's good to write now. 17 into 1 is already there. Now I'm telling about this person. Now this will be now gamma saturated. So don't write 17 here. This portion is also due to capillarity. This portion is also saturated. Saturated. Even water table is not there here. So now gamma sat into the thickness of the capillary fringe is 1 meter. Let us see now. This is 1 meter. So gamma sat into 1. So one can easily write now gamma sat into 1. It is now 21 into 1. So 21 into 1 is obviously 21. So we have 17. 17 plus 21. So that is the story of 38. So now this is going to be constant 17. Then this is also constant. Now here you see uh, what is going to be happen now. Here it is 21, 17 plus 21 up to here it is 38. Now as usual we can able to calculate now. It is a saturated soil. Now I can able to calculate now 21, the depth is 8. So 21 into 8, so it will be 168. So now 168 plus 38, it gives now 206. So this is the total total stress distribution diagram from top to bottom. This is total stress distribution diagram. Now let us discuss pore water pressure distribution diagram. Now here you see pore water pressure. As I told you, this will gives in capillarity, it gives negative minus gamma W into HC, 9.81 into 1. That's why he has written 9.81. Now let us come to the uh, below the capillary zone. Now you see gamma of water into height. Here it is noted. It is 8 meter. You know it is 8 meter. 9.81 into 8, which gives 78.48. Now we can able to calculate sigma dash. Many of us knows how to calculate effective stress. Sigma dash is equal to sigma minus u. Sigma minus u. Here is 0, 0, 0 minus 0, 0. Now here you see I have 17 minus 9.81. So that gives 26.48. Let me tell you, because this is minus 9 point, capillarity creates negative pore water pressure. So here I can tell you sigma dash is equal to sigma minus u. Here you see capillarity produce negative pore water pressure of sigma minus gamma W into HC. Now it's good to discuss now. Minus into minus will become plus. Now I can write sigma plus gamma W into HC. So that's why. So pore water pressure will what I say, it is negative. So total what happen effective stress will increase. So that I point I would like to write here. So due to due to capillarity rise, effective stress is going to be increased. So due to capillary rise, it's good to write now due to capillarity, due to capillarity, effective stress will be increases. So that is very important note we should uh, we should mention here. Capillarity will due to capillarity, effective stress increases. Effective stress increases. So thank you all.